Here's the demo for our final project. The first screen that the user sees upon launching the app is the user login screen, where they are prompted to enter their username and password, or register for an account if they don't have one already. I'm going to pretend like I don't have an account, and I'm going to go ahead and register as a student. Hit register, specify that I'm a student. Now I've successfully registered, I can go ahead and log in. I can go ahead and also log out if I want to maybe register as a professor, if I'm a professor. There we go. Now I have a professor account, and I can go ahead and log in and view the app from the perspective of a professor. And that's about it for the login page.
Okay, I will be demoing the creation of code blocks within our basic flowchart drawing app. So the first feature I'm going to show is just loading something from the cloud. So this is an example with every type of shape or code block. So in this flowchart, we have a start, some kind of variable declaration, a function call, then print, if, and this if statement branches into a loop or an instruction, and this loop goes to an instruction and then back to itself. And then this instruction block right now is just hanging, but we can add as many connections as we want as incoming connections. But code blocks will, for an example instruction that only expects one to be able to come out. It's not an if statement, so it won't let you do that. And the loop block similarly only has two connections out, as well as with the if block, as you can see here. But as many connections as you want can enter into a stop block, which is to be expected because that's how flowchart diagrams work. And say I want to upload and save my changes to the cloud. First, I would save the diagram. You'd call it everything2, and upload everything2. And then if I go back to courses and hit cloud again, everything2 will be loaded from the cloud. Then say I create a bunch of code blocks and I want to get rid of their connections, I can undo. And then their connections are completely removed. And then if I wanted to change the text, I can change the text to anything. So I can change the int I equals 9. And you can do that with any of the code blocks. And you can clear the flowchart as well. And if I want to load something I saved locally, that's how you do it, everything2. Again, because it is saved locally and then saved in the cloud. And yeah, that's it for the sandbox. I will be demoing the flowchart or the flowchart to code problems. So here's a flowchart. Our job is to convert it into code. And say I don't know what start should be. Okay, start is just your standard main method. And what this does is it just compares this against a list of lines. So if I type this all out, and A equals 2 and B equals 3, and these lines are white space sensitive. So the white space does matter when you're typing these. In the future, we would want to implement the parser and lexer from the compiler assignment. Then we can actually you can type whatever you want as long as it evaluates the same flowchart. And then for stop, If I don't know what a stop would look like, okay, lets me know it's a bracket. If I ask for help again, it will just tell me I'm right, because this is the code. This is the code to make this flowchart. If I delete this, ask for help, it'll tell me that there's a mistake on line 4 and what I'm missing. Let's see. Okay. And okay. And I can add empty lines, and those won't count against me. But any other type of line does matter with the prearranged list of lines. And you can go next. These print blocks should be slightly moved apart. There's 2 print blocks that overlap a little bit. But yeah, this is the next problem, and we would just continue converting the flowchart into code, and that's our flowchart to code problems. Okay, I will be demoing the conversion of code into a flowchart. So this is an example of a code to flowchart problem, and here we can see is the code that we need to convert. Also, it prompts for cyclomatic complexity, and it times how long it takes you to complete the problem. You can hide it, but it's still keeping track of your time. And I have this the solution saved locally into my computer, so I'll just load the solution. And if I load it, you can see that it'll say the diagram is correct, but no cyclomatic complexity was given. But to just show off the tutoring capabilities, I will pretend I don't know how to create a diagram. So if I just hit submit, it'll say the diagram is not correct. Submit just tells you if you're right or wrong, but if I want help, looks like a start block is missing. What does the start block do? The start block tells the program where to start. Okay. Help. Okay. A variable labeled int a equals 2 is missing or not properly connected. This code block should be executed after the start block labeled start. Okay. Variable. I'll connect it there. Then, okay, I forgot to label it. Change text int a equals 5. And then, okay, it should be labeled int a equals 2. Okay. Some white space here. Okay, so int b equals 3 is missing, so we can, just like a normal program, you can have as much white space as you want. I'll change the text int b equals 3. And print. Okay, and help. Oh, I forgot to declare the variable. But you get the idea with this, it guides you through the problem. So if I load the flowchart again, and then I add the complexity, it is right, and this turns green, and it tells me it's done. And then the tutor will tell you both are correct as well. Same thing if you hit help. And we'll give you a little message saying good job. Then go next. And we'll load the next solution. Submit. Forgot the complexity. Surely it's 1 because there's one if block. It's not correct. Ask for help. The expected cyclomatic complexity is greater than 1. The cyclomatic complexity is the amount of paths the program can take. 1 plus the number of loops plus the number of if statements. Okay, so it should be 2. Okay, that's right. And then if I load the last solution, and knowing that it's the number of paths, which is loops plus 1 plus if statements, there's only 1 loop and 0 if, it should be this. Okay, completed the assignment. And if I was to delete this statement right here and ask for help, it will tell me that T1 equals T2 has no connections entering into it. It will tell you you're wrong if there's any code blocks that aren't accessible. And then if you ask for help again, it'll tell you that the variable is missing, which it is because it's gone. And that's most of the flowchart. There are some more specialized hints that it can give where multiple cases are occurring, but that's the general idea, is it'll guide you through the problem. And if you go back to courses, it'll now say that this assignment has been completed. Okay, this is our final use case diagram. So we have 2 primary actors, a student and the professor, and 1 secondary, which is the server. It just reacts to some of the actions that the student and the professor can do, which are authenticate credentials, load flowchart, and save flowchart. So you can save a flowchart locally and load it locally, or you can save it to the server and load it from the server. So the server would choose to react to those save actions if you choose to save and load from the server. Otherwise, if you don't choose to save and load from the server, you would save and load locally, which the server would just do nothing. So its response to saving and loading locally would be nothing. And it is required for authenticating credentials. And then the student and professor have a lot of overlap because they can both create flowchart diagrams, and most of these use cases are dedicated to creating use case diagrams. Some of the unique things, or for creating flowchart diagrams, some of the unique things the professor can do is create problems, delete a created problem, and create a class. Unfortunately, these aren't connected to the server quite yet, so hence why there's no connection to the server actor. The server doesn't respond to these changes are not saved. And then similarly with completing assignments and problems, these are not saved to the server. That would definitely be something we'd want to implement in a future sprint. Some things unique to the student are completing a problem for both problem types to code to flowchart and flowchart to code, and then only the flowchart to code problem has cyclomatic complexity involved, and you have to do that to complete the problem, and that's why there's the include case being used there. And then inheritance is used for completing a problem because there's 2 problem types, getting help for a problem because there's 2 different problem types, and both problem types need different types of responses for help. And then same thing with getting an answer to know if it's correct. From the user, it looks like they're the same, but behind the scenes, the grading for the flowcharts are different. For both problem types are different. And then the best use case for inheritance is this over here. It's just drawing the code block for the screen. And this is pretty similar to our UML diagram, where we have drawing function block, drawing variable block, and so on with all the code blocks. And then just over here, we can see more of the stuff for creating the flowchart. So clearing the flowchart, dragging blocks, and that kind of stuff. Another thing that stands out is messaging the professor. This is unique to the student. Unfortunately, it is not connected to the server. It just prints the message in the terminal right now. But if on another sprint, we would like this to be connected to the server, and then the professor to be able to send a message back. And then for them to both be able to receive messages. And that's the use case diagram. Okay, for our process, I chose to choose 2 stories to show for each sprint. So for sprint 0, which is the first and last sprint of last quarter, we had clear flowchart and draw end block. Sprint 1 of this quarter, we had create code based on a given flowchart and create a flowchart based on a given code snippet. For sprint 2, we had authenticate users to SQL Server and allow users to edit code block text. In sprint 3, we had submit flowchart to code problem to see if the user's answer is correct and get help for flowchart to code problems when the user is stuck. For sprint 4, we had evaluate cyclomatic complexity proficiency for code to flowchart. And for sprint 4, we also had, as a user, I would like to know how much time it takes to complete. And then for the stories, we have 39 stories in total, and all these stories were attempted to some degree. And we had 38 stories that were mostly features. This is about 97% of all stories. And we had 1 story dedicated to maintenance. And then we had no stories dedicated to the knowledge acquisition or technical activities. And then some stories did have technical activities as tasks, such as converting the SQL server from a local database to a free database in the cloud. And we had 0 stories in the product backlog. And then for calculating points, we calculate on the scale that Taiga used, so 0.5, 1, 2, 3, 5, 8, 10, 13, 20, or 40. And we just used one of those categories for the scale. We didn't combine UI or backend. For the most part, I think we did just assign one value to one of those categories, and that was how the scale that we used. And we calculated or estimated how many points on the scale it would be by creating all the tasks and all the stories first, and then looking at the tasks that compose each story and then estimating in our head how much time do you think it would take, how complex is the task, and a combination of those 2 things would dictate how many points we assign it. The highest point stories were enable assignments to be completed at 27 points and draw code blocks to the screen at 24 points. And the total story points of attempted stories were 193.5.
I'm Patrick, and I will be talking about our sprint summary. So this quarter we had 4 sprints, and these are our Burndown charts.
A model view controller outline for both the student and professor views. We had both of them connecting to an SQL server through a control handler, an SQL control handler. And then we had our views and controller updating our knowledge sources, which were problem repositories and singleton repositories mostly. And then those would be modified via a proxy, which was our Blackboard, which would be an intermediary between the creation of the code blocks and the updating between our knowledge source. And those differed between the student and professor, so we had 2 separate views for those. For our packages, we only had 1 package, and the reason we only had 1 package was because we didn't realize we could create multiple packages until the last sprint, and by that point we just needed to get the product up and running, so it didn't make sense to add multiple packages. It would have added too much complexity in the small amount of time that we had. For our product design, the key for this UML diagram is that our controllers are red, our views are green, and our models are tan, and then any Java utilities are blue.
As you can see in the bottom right, there are all the views which interact with each other. As you get to the middle, you have intermediaries, such as, for instance, over here is all of our shapes in our diagram app for the individual, for the creation of diagrams and flowcharts. And then at the over here, we have more of our SQL. The views, the controllers for our SQL database, and then up here we have our repositories, which is our singleton design patterns, which have steady state data transaction between the entire project to make sure that it's permanent and it's only one instant. And so that's sort of how this UML diagram explains the product. As far as how easy is it to modify, reuse, and extend, a lot of our classes are extended from abstract interfaces. For instance, our repositories are abstract of a repository interface. Our views are abstract from an app page interface. Our code blocks are extensions of a shape interface or a shape class, which then has more extensions for circles or lines and things like this. We used extensively the singleton, decorator, factory, and observer design patterns, and so overall it's very easy to expand upon any of these features because a lot of them were abstracted initially from the inception. It's also very intuitive, the naming conventions along with the method creations and things like this, so it's pretty easy to modify or reuse components. For instance, if we want to add new shapes, if we want to add new views, if we want to create different repositories, we could do that very easily using the current things that we have. For some of the instances of the design patterns that we use, we have our decorator, our singleton, and observer. For our decorator, for instance, we had a shape. We didn't want to define a draw method for the shape because we wanted to extend from the shape class, and then those extensions from the shape class may have individual extensions themselves. For instance, a line would extend a shape, but then we might have perpendicular lines or parallel lines or arrows extend from the line. So we didn't want to define a single draw method for the shape that would be only implemented in a line. We wanted to add it in as a decorator so that we would be able to clearly define different methods for that, different behaviors for that. For the singleton, we use the singleton for any repository, so we would have a repository interface that would then they would all implement, and that would make it so that we could have steady state data over the entire project for things such as the code blocks. We didn't want multiple instances of our data repository. We didn't want duplicate views or code blocks happening, so we had that as a singleton along with the problem repository and the state repository for getting drawables, getting currently selected items within our diagram map. And then for the observable, we had, for instance, we needed our problem repository to be observable and updated through our diagram app, which was an observer. And that way we could have the diagram app manipulate the steady state data within our singleton problem repository. For instance, if you want to update which problem the user is on, which problem is currently selected, things like this, we needed to make sure that we had the observer and observable interface design pattern used.
This is Alex with part 2, the product. So in general, we had clean source code, good Java doc coverage. We had some minor issues with do not repeat yourself and keep it simple. So we had 2 different classes for displaying side panels with similar components, which was repeating ourselves, and our teaching app was both a view and controller, and sometimes we would pass views to a controller class as a parameter, which isn't really keeping it simple. But other than that, it was pretty good. We had decent metrics, 3970 lines of code, 3275 effective lines, and 2242 logical lines, with a maximum cyclomatic complexity of 20 and a minimum cyclomatic complexity of 1, with an average of 3.25. Then for some structural metrics, we had an average abstractness of 0.1, an average distance of 0.4, and an average stability of 0.55. And there's the instability versus abstractness chart. So you can see not too much stuff in the painful zone. As for our testing, we had unit testing for code block, the data repository, state repository, and the grade flowchart and grade cyclomatic complexity classes. And we had a total of 47 test cases with 93% statement coverage for the data and state repo classes, 74% statement coverage for grade cyclomatic complexity class, and 77% statement coverage for the grade flowchart class.
So this is our cost estimation model. Came out to be about 10 person months, with best case being 2.4 and worst case being 590 person months. And some of the reasons we had a pretty fast estimation was we had a cohesive team with continued personnel from last quarter, and we were all familiar with the platform, familiar with Java and Java Swing. We had a pretty flexible work schedule as well, and our project didn't have any complex systems, and there were no performance regulations such as time constraints for the time the program had to run in, and it wasn't a very large program, so it didn't require lots of storage.